Yeah, sorry about that. So it's the same talk, it's just a different title. So thanks again for inviting me and for allowing me to force you to listen to me twice. I don't get to do that very often. And by the way, I've had a wonderful time here visiting, so thanks for your hospitality. What I'm going to talk about is something. It does involve what the other title said. It's about local minimax testing. So first of all, let me tell you about my colleague here, Sivaraman Balakrishnan, is a young faculty member in our department. He's an amazing guy. He's the one who got me interested in this topic. And it started this way. He said, Larry, there's some interesting work on multinomial inference being done in the field of theoretical computer science. And I said, multinomials? Like, we've solved that 100 years ago, didn't we? And he said, no, we really should look at this. And he was quite insistent about it. Finally, I started looking at it and realized, actually, I think you're doing some interesting things there. So that's how we got started on this. And there's really, that's, well, does it matter that the title of every slide is going to be cut off? I guess it doesn't matter. I'm going to infer the titles of the slides. So, this is just showing you some.
Yeah, it happens like
that. In this slide. That's what it works. Okay. No, did it go?
Yep.
Oh, it's working. Okay. It's good like that. I think you guys can read that. All right, so this is just motivating here that we're going to be talking about, first thing I'll talk about in preparation is multinomials, but we're interested in cases like this where the number of categories is very large. But not only that, there's been a lot of work in statistics about what happens when the number of categories is large, but we don't necessarily want to be in the regime where you have normal asymptotics. So if you assume that the number of categories is large and say, but I'd like things to converge to distributions I'm familiar with, you need to add extra assumptions to the multinomial. We don't want to do that. So this is part of what I call my mission that I've been on for the last few years, which is to try to eliminate all assumptions in statistics. Now, of course, that's impossible, but I am interested in what are the weakest possible assumptions. And so in this regime, you're going to see we're not going to assume extra things in the multinomial that will make life easier for us so that we can get like a chi-squared or normal or something like that. And so we really want to understand what's the fundamental limits of this problem, and without adding extra assumptions to make things easier, which unfortunately does make things very difficult, but is interesting. So in particular, we want to get rid of a common assumption in a lot of literature, which is that if you're doing a hypothesis test, you might be testing, for example, uniform, and that D might be fixed, and then there might be other D, the number of categories might be fixed, and that there might be other structural assumptions that we don't want to make. By the way, I should have prefaced this by saying the whole talk is going to be about hypothesis testing. Now, I actually don't like hypothesis testing, and in fact, I always tell my students, don't use hypothesis testing. It's one of the most overused statistics tools, and it causes all kinds of problems like the reproducibility crisis in science and so on. So why are we doing this? Well, this is sort of the tip of the iceberg. We're trying to study these regimes that are difficult to deal with without making extra assumptions and ask questions like, how hard is this problem really to solve? What are the best estimators and so on? It just turns out that a very clean place to start with is hypothesis testing. So think of this more as the first step towards what we really want to do, which is to get confidence sets and estimators and things like that. And it's just that a good way to begin is by looking at hypothesis testing. But this is just the beginning. I'm not suggesting that one should just test the hypothesis and declare victory. So I'm going to first talk about the multinomial case because that's the background for this case, which is testing a density, but we put this wiggly thing on there because we're going to address what you must, again, we think this is a solved problem. I draw n observations from a density, and I say, did it come from this density? very old problem, completely solved. Well, it turns out it's not quite true, much to my surprise. In particular, when we allow the smoothness to change with the sample size, we want to allow for very unsmooth things. We don't want to make the traditional smoothness assumptions, because that's just an assumption. It's something we just do for mathematical convenience, but no one says the density has to be smooth. So our goal here is, again, we're going to see that certain assumptions that are made in the literature about like uniform, oh, I can do this. The uniform null is often assumed, bounded domain, smoothness assumptions. We're going to try to weaken all that stuff to the degree that we can. And it turns out some interesting things happen. At least I hope you'll find it interesting. So here's the setup. We just have, it's the simplest possible statistical problem you can imagine. That's like the beginning statistics problem. M observations from a distribution P. I give you a fixed P0, not even a family of distributions, just a fixed P0. And I just want to test the null hypothesis that P is equal to P0. And the alternative is going to be, and I was talking about this with Dave earlier, that P, the distance between P and P0 is bigger than some number epsilon. And I'm using the total variation distance. And what is the total variation distance? It's just it's just P of A minus Q of A, the maximum over all events. And why am I using this distance? Well, first of all, in terms of multinomials, it's a very interpretable distance. If I tell you the total variation distance is 0.2, that means these two multinomials differ on every event by at most 0.2. So it's got a very simple interpretation. Whereas if I use like the L2 distance for two multinomials, what does that mean? What does the L2 distance being 17.3 mean? It's not very interpretable. But of course, the truth is we've actually worked this out for lots of other distances too. But I'm just going to focus on this one distance. So every question I talk about today could also, of course, be addressed in other metrics as well. And it turns out the answers depend very much on the metric you're using.
Just make sure the P here is a class of the distribution or density family, or
this is just the alternative. No, so this is just the data come from a fixed P unknown. So that's just one distribution, but it's unknown. And the null is some fixed specific distribution. Yeah. Of course, there's also extensions to all of this, to multiple nulls and so on. But this is all just one fixed distribution. Things turned out to be surprisingly difficult even in this setting. So as I said, TB, total variation, is a natural metric here to use, but you need some sort of assumptions. You can't actually test this hypothesis. So in general, testing this versus this in great generality, there is no consistent test, as Tom showed that many, many years ago. But we're going to have a little bit more structure than that. So there'll be two cases. The beginning case, again, will be multinomials. So I just have a vector of probabilities P, the usual multinomial. It sums up to 1, and I'm always going to use D for the dimension, so the number of cells in the multinomial. And D you should think of as being pretty large. The other case that we'll get to then is for densities, we want to assume the minimal amount of smoothness. And actually, we can even be more minimal than this, but this is, for this talk, we'll call this minimal, I guess, which is the set of all densities that satisfy a Lipschitz smoothness constraint. But we're going to allow this Lipschitz constant to possibly get larger than that. I think I say that right here, yeah. Because a lot of the literature, again, focuses on things like, again, the uniform null, D is fixed, and so on. Or here, a lot of the work that I'll refer to assumes a uniform null, bounded domain, L is fixed. We want to eliminate all of those assumptions and see what happens. And the way I'm going to express it again is in terms of hypothesis testing, and in particular in terms of the minimax rates. But I think hopefully it's capturing something more fundamental, which is just how does the difficulty of the problem depend on these things. So just a couple definitions. I'm good doing hypothesis testing, so I am going to restrict myself. So a test will be denoted by phi, and the probability of type 1 error, we're going to restrict ourselves to tests that have, say, some given level alpha, as usual, under the null. The null here, I wrote, generally could be a set of distributions, although mostly I'll focus on a fixed distribution. And this is the set of all level alpha tests, and now I'm going to do the usual minimax thing and say, what's the worst case? So the risk of a level alpha test is It's maximum type 2 error. So I'm just computing what's the probability of failing to reject when the alternative is true. And I'm doing this, I'm taking the soup over all things that are epsilon. So I'm taking all things epsilon far from the null and say what's the worst type 2 error. And that's going to be the minimax risk. And then I want you to notice something, that since we're in a hypothesis testing situation, I'm standing at P0 and I'm asking what's the risk around everything epsilon far away. That could depend on the null. That's why this is called local minimax. So this risk actually depends on the null. The way minimax theory is usually done is to then oh no, I'm still on local minimax, sorry. One more definition. Now I want to ask the following thing. I'm testing the null P0 versus everything epsilon far away, and the way I'm going to summarize things is how far do I have to move away until I get non-trivial power. So there's going to be a phase change that if I'm too close to the null, you have no power, and if I'm really far away, you have power 1. And we're going to define epsilon to be just how far enough you have to be before it becomes distinguishable. The power is, say, 80% or any given number. So what we're really going to be looking at is this rate, epsilon n, which is how far you have to be from the null before you get power. That's the fundamental quantity we're interested in. Now the point I was going to say is that this was all focused on a specific null hypothesis. Now we can do this over the whole space, right? I can take the worst case over all possible nulls. That's just the usual minimax risk. So just to repeat that, usually, we compute the minimax risk. The way you compute it is you pick a distribution and you look what's the worst case around that distribution. Usually the answer doesn't depend on which guy you picked. It's a global thing. Turns out that's not true in these more difficult cases. That we're going to see that the minimax risk over the space of multinomials varies considerably depending on where the null is. And so that's why I'm going to keep referring to this global minimax rate, which is what's the worst case over the whole simplex, and the local minimax rate, which is what's the worst case, or how far away do you have to be for that particular null distribution. So that'll be the local versus the global minimax rate, whether I put the P0 in or don't. And we just want to ask, what's this number? How far do you have to be from the null so you can test it? I'll just skip this. Skip that slide. Okay, it's not important. I don't know why I put that. The last comment, though, is important, which is, again, for sufficiently homogeneous problems, the local and global rates typically are the same, which is why people don't usually distinguish them. But it's not going to be the case here. Okay, so let's start with the multinomials. And of course, the history, I can't put the history of multinomial inference on even 20 slides, it's so long. But there were people like Karl Morris, Steve Feinberg, Andrew Barron, who looked at, and many other people, who have looked at the case where the number of cells is increasing along with the sample size. Or another way to put it is just the number of cells is large. And minimax rates have been worked out. I think Liam Paninsky, who some of you may know is at Columbia, was one of the first actually, I think, to nail the rate. And as I said, there's a lot of follow-up work in computer science, surprisingly. Not machine learning, by the way. There's another part of computer science, TCS, theoretical computer science. I would say that's the community mostly doing the multinomial work. So here's some notation. We're going to have this multinomial vector, P1 up to PD. And without loss of generality, let's just assume I've ordered them so that they're biggest to smallest. And I'm going to tell you now what the global minimax rate is, because I'm not going to spend much time on that, which is epsilon, the global minimax rate, how far you have to be before you get substantial power, is d to the 1/4 over root n. This, if you've never seen this before, this should shock you, because if you think about it, what does this mean? And think about what n would have to be if I switched n and epsilon here. It's saying that n can be much smaller than the dimension, and you can still have substantial power. So if you think about having a multinomial with a large number of categories d, what that says is I can give you very few observations. Most of the cells are empty. You don't even see them, and yet you can still have high power for testing that null. And that's actually pretty surprising. So this, to me, this is very counterintuitive. This is what it comes out to be. But what's happening basically is occasionally there's collisions, meaning with small non-trivial probability, you get two things in a cell. And that's enough information already when you see how many collisions there are to tell whether you've got the right distribution or not. So this is actually a rather surprising thing. But it also shows you that it's quite different. Testing really is different from estimation because this is much faster than the estimation rate, which would be more like root D over N. And so testing and estimation in this world actually turn out to be quite different. But what about the null? This is not local. I haven't said anything here about what the null is. I'm just saying no matter what the null is, you can always test things that are D to the 1/4 over root N away. But this doesn't depend in any way on the null. What if I try to say, are some nulls easier to test than others? And this is where things get really interesting. And this is how we first got into this, was we came across this paper by the Valiants. If you don't know who the Valiants are, this is Greg Valiant and Paul Valiant, or maybe that's Paul and Greg, I don't know. And their father is Les Valiant, who's a very, very famous theoretical computer scientist. Won the Turing Award, or whatever the big prizes there. And this is his sons, and they're theoretical computer scientists too. And they have this paper in 2014, which does the following thing. First of all, it turns out you need to divide the multinomial. Think of the multinomial, remember I'm ordering it. I'm going to divide it into the bulk and the tail. So B is the high probability atoms, and Q are the low probability atoms, the tail. And there's some cutoff point sigma, we'll just call that sigma. So I'm dividing it into two regions. That turns out to be important in this. You have to separate the high probability atoms from the low probability atoms. And then you compute this very, very surprising quantity, which is you compute the 2/3 norm of the bulk. So you take P to the 2/3, you sum it up and take it to the 3/2. I've never seen any other place in statistics, or I can't think of any other one, where the 3/2 norm arises. It's a very weird norm, right? But this turns out to be critical for this, rather surprisingly. I actually asked Greg Valiant, how did you know to use the 2/3 norm? He said, we didn't. He said, we just kept trying every norm until the calculations worked out. And in fact, he said, one of us worked on the upper bound, one of us worked on the lower bound, and we just kept working and trying different ones until we got the same answer. And it came out to the 2/3 norm. Now, when you actually work through the minimax proof, it sort of emerges, well, it's not quite so mysterious where it comes from, but it's far from intuitive or obvious, I guess. And basically what they showed was that, actually let's just go to roughly speaking, the minimax rate for testing whether the data came from a particular multinomial, P0, is the 2/3 norm over n square root. Very surprising. I mean, at least to me this was surprising. I never would have guessed that was the answer. There's actually a lower and an upper bound, and it's essentially tight. I'm just constant here. So this is pretty much it. I mean, that's the answer. It's not like the 2/3 norm came up because they did an analysis incorrectly and the bounds are weak or anything like that. This is actually the correct rate. And in fact, I never even said D had to be finite at this point, right? This 2/3 norm could be a well-defined finite number, even with infinite many categories. So in some sense, it's not really the size of the multinomial that's driving it, it's the shape of the multinomial, which is what the 2/3 norm is measuring. And what is that? Well, it turns out that the 2/3 norm can be anywhere from 1 to root D. And roughly speaking, the sparser the multinomial is, by which I mean you have a few large p's and then it dies off pretty quickly, you're going to get something close to 1. Whereas if it's the worst case is uniform, you get root D and you get back that rate that I had up earlier. So what this is showing you is if you think about the uniform, the multinomials on the simplex, and you ask, I want to test the null distribution, the hardest one is in the center of the simplex. That's the hardest case. But if you happen to have multinomials near the edges of the simplex, you can actually get very high power even when D is very large. And so I think that's pretty revealing about the problem. I was talking with someone earlier about what use is minimax analysis really? Because it's not like I'm going to go and analyze the data differently because of the minimax results. But this is an example, I think, where it just does actually reveal something about the structure of the problem and helps you answer the question, what makes the problem more difficult or what makes the problem easier? And here, in some sense, you can see it's, the shape of the distribution. Things that are near the edge of the simplex, which only have a few large atoms, are going to be easier to test. So again, this is the uniform case. This is a special case that gets us back to that, but that's the worst possible case. Okay, and in particular, if you had a very sparse null, like if you only had S categories with positive probability and everything else was 0, well, that would be an extreme case. You'd end up with a rate like S to the 1/4 of root n, which would obviously be a very, very fast rate. So you can test that easily. That's pretty intuitive. If my null is that most of the categories are 0, it should be fairly easy to test, because all you need to do is see an observation somewhere in the tail, and you know that the null is false. So a lot of I think I'm going to show you some of the simulations we do are for power law multinomials. We provide a lot of information where the null goes down in a power law. And we're going to see that this has an interesting 2/3 norm, because it's not nearly as small as the sparse case, but it's not nearly as bad as the uniform case. So we see some really interesting behavior. And of course, just to remind you, you could be talking about Poissons or other things with even infinite support. All right, so that's the minimax bound. That says the best you can do in principle is the 2/3 norm over n square root. How do we actually test it? Is there a test that achieves that bound? And their paper does have a test. It actually involves two tests. One, to take care of that tail piece I talked about. That's not so interesting. I'm going to ignore that. I want to focus on the main part of the test. And the main part of the test looks really interesting. This part looks, this test statistic looks a lot like our familiar chi-squared statistic, with two important changes. The first one is it's centered. So this just basically makes it centered to have mean 0 under the null. This part actually, don't worry too much about that, but there's this 2/3 again. So, in every textbook in statistics, the chi-squared test, we divide by p0. And that turns out to be the wrong thing to do. We've been doing the wrong thing for 150 years. So you should actually be dividing through by p0 over the 2/3. And I'm going to show you the simulations that actually makes a big difference. And so what they did was that they proved that this actually achieves this minimax rate. And the analysis is somewhat involved, because what's happening is, unlike, again, a lot of the previous literature on high-dimensional multinomials, if you look at the test that people construct, they say we're going to test a high-dimensional multinomial, plus we're adding the following conditions on the multinomial. Those following conditions are what allow you to now take your test statistic and show it converges to a normal or some useful distribution. We don't want to rule out anything on the simplex. We want to allow everything. And it turns out with these, without any further restrictions, you can't actually say that this is convergent to any particular distribution. And so you can't rely on normal asymptotics and chi-squared. And so the analysis is kind of difficult and technical. It involves doing very, very careful bounds on the moments of the statistic and so on. Okay, let's just skip ahead there. Here's a couple simulations. So just to show you what actually happens in practice. And by the way, I should mention that we have two papers on this. One, which is a very technical paper, which is, we just sent a revision to the Annals. But we actually wrote a review paper about this in a special issue of the Annals of Applied Statistics that's coming out in honor of my late colleague, Steve Feinberg. And so if you want to see sort of a summary of all this stuff, that's actually already on the web page of the Annals of Applied Statistics, the review paper version. All right, so this is a null. This is the hardest case, is when the null is uniform. And what's the alternative? Just to give you an example, we're going to take the alternative to be sparse, meaning that only a few cells are different from the null. And what this is showing you is the L1 distance, that epsilon, and then I'm showing you the power. So in this case, while the chi-squared test, our favorite test, or common test, does very well. Does pretty well. You can see that the power increases nicely. The likelihood ratio test also has reasonably good power. This this 2/3 norm test, so I don't have a good name for the test, doesn't do quite as well, but it still does, it's okay. I mean, as the distance increases, the power increases, it does lose a little bit. After all, it's minimax, that doesn't mean it works best in every situation, it just means it's worst case behavior at the best, right? So in the uniform, in fact, there's lots of other tests we've tried here, and they're all performing fairly similarly. But now let's leave the uniform null. And so this is a power law null, so I mean that the null distribution is a set of multinomial probabilities that are decaying with a power law, like this. And now you see, really startling behavior. This is the chi-squared test and the likelihood ratio test as a function of the L1 distance. They basically are powerless. Whereas this test has beautiful power. And so you can see it really, really matters, actually. I mean, the distance is rather striking. And our paper has lots of other simulation results. This is basically what we always see. As soon as you leave the uniform case, you really shouldn't be using all the test statistics that we're used to using. You should use this test or another test I'm going to tell you about in a minute. This is, by the way, the usual chi-square test. I just centered it to have mean zero, something we got used to doing from all these calculations. But basically, the denominator is the usual one. And so this is just the usual chi-square test. But the problem here, and the reason why things fail, is that whenever the probabilities get small, it just turns out that the variance dominates the statistic, and it just kills the power. That's basically what's going on. And the same thing happens with the likelihood ratio test, and you can think of other test statistics like an L2 test statistic and so on. They have the same test. These tests are not even globally minimax, let alone locally minimax. So it's kind of surprising when you think about it, that all these years we've been using these tests and we didn't know that. You might wonder, is there a more direct way to just adjust this without going through all that stuff, 2/3 stuff? And there is. In our paper, we have another test, which is globally minimax, but not locally minimax. But it's a bit, I kind of swept some details of that 2/3 test under the carpet. There's actually a tuning parameter I didn't talk about, and so it's a little bit difficult to implement in practice. But it turns out, a very simple fix. This is the usual chi-square statistics, the centering term, but all we've done is, instead of dividing by P0, we divide through by the max of P0 and 1 over D. So basically you're truncating that bottom so that when it gets close, starts to get small, you don't use the bottom anymore. And what we showed was that this clipping, as you might call it, is globally minimax. So even if you just want to keep using chi-square tests, just make this one small tiny change to it, and it's going to save you. It's going to give you very, very high power. And it's much simpler than their test. Again, I didn't go through all the details of their test. This is much simpler, and let me just show you how well it works. So this again is the chi-square test, and this is like the ratio test. This is the 2/3 test, and our test is in red, and you can barely see it there, but it's right there. But it actually does better than their test in that case. But now let's look at that power law situation. And again, you see here the chi-square test, likelihood ratio test. Their test we know is optimal, so their test is the 2/3 one. Ours was only designed to be globally optimal, not locally optimal, but even still you can see it does really, really well. So this is a pretty good practical compromise. It's just as easy to compute as the usual chi-square test. Although it's not locally minimax, it's globally minimax, and it has very good power. And by the way, I should say, to get the cutoff point, though, you have to simulate from the null. You can't rely on asymptotics. But that's not a very expensive calculation.
If you change your norm from total variation to others,
The whole story changes. So if I was not using total variation, I use a different distance, everything changes. So unfortunately, and we're writing another paper on that, the story is different for every single distance. And I would love to have a unifying theory that says, a general thing that automatically adapts to the metric or something. But we don't have that right now. We're doing everything on a case analysis. Another way to get local,
Could you describe the simulation that you use for the alpha level?
The simulation, since don't forget the null is a known fixed distribution. So you just simulate n observations from the null, compute that statistic, and repeat. And then you just find the alpha cutoff point.
So in the uniform case, is the bulk uniform uniquely defined? The B sigma.
Yes, in the uniform cases, the bulk, well-defined, it's just empty.
Oh, okay.
Another question that might come up is there a simpler way to get a locally minimax test? I gave you a global one. And there is. Actually, let me just put my timer out because maybe I think I'm going to skip this because I don't want to run out of time. I want to get to the densities. Anyway, so I'll skip this part. If you want the slides, I'm happy to get into it. But roughly speaking, here's a simple way to get local minimaxes. I'll just describe it by hand. So if this is your multinomial, you just chop it up into pieces where it's approximately uniform. Then you do any test you want, because it turns out for the uniform distribution, it turns out all the tests have roughly the same power. Do any test you want within these uniform bins, and then take a Bonferroni correction over it. And that's actually locally minimax. You actually lose a log term, but I never worry about logarithms. So. All right, so I'm not going to talk about that. Now let's move on to densities. So let's just go back to the model. I'm going to assume we're looking at the space of all densities. They satisfy this Lipschitz condition, that's the smoothness condition. And for now, I'm going to focus on the one-dimensional case, but everything I'm about to say applies arbitrary but fixed dimension. We're not letting the dimension of the sample space increase. D is some fixed number, and we'll just take the D1. And so Yuri Inkster was this, is he Russian or Lithuanian? Something Russian or Lithuanian or some convex combination of those things or something. He really set the standard for all. He worked out an incredible amount of theory about minimax testing throughout the years. I think he only recently passed away, if I remember, maybe a year or two ago. And so if you want to know anything about testing in a continuous case, the first place you look is Inkster's papers. And he did the case where you're on the unit interval, the null is uniform, L is fixed, and he said he worked out the minimax, right? And the answer is 1 over n to the 2/5. So you have to be in total variation distance, 1 over n to the 2/5 away from the null before you can detect a difference. And he kind of hinted that, well, this assumption is sort of innocuous. But it turns out it's not. Things change quite a bit. First of all, I should mention that recently Arias Castro has a paper, I think it's on the archive, I'm not sure if it's appeared yet, extending Inkster's work to D dimensions, and you get similar results. And you might think, how am I going to deal with non-uniform cases? And my initial instinct was do an inverse integral transform. I just take the CDF, transform it to the unit interval, do a uniform test and transform back, and that doesn't work. First of all, you're changing the smoothness assumption implicitly when you do that. And also, we don't want to have to keep L fixed. We want to allow L to possibly grow so that we can allow for very unsmooth densities. This is a case, by the way, I have to say, my young colleague. It's great to work with him because every instinct I had in this problem was wrong. So, like my initial instinct, I said, this problem would be easy to solve, just do an inverse integral transform. He said, that's not going to work. I said, yes, it is. And then he came back and I said, it doesn't work. He was always right about this stuff. His mind hadn't already been fogged up with years of thinking a certain way. So anyway, we figured out what it is, and my colleague did most of the hard work on this. Again, there's a kind of a bulk and tail calculus separation we need to do. But the interesting thing is, what is the functional that drives the local minimax rate? So with multinomials, it was the 2/3 norm. So you might guess, well, maybe it'll be the 2/3 norm of the density. It turns out it's not. It's the square root. And so it turns out that the integral of the square root over this bulk region, over this high, this is the key functional, that everything depends on this. And so this is the minimax rate. It's L, which is the smoothness, which can now be arbitrary to change with n. This functional t, which is capturing the local difficulty of the problem. And then here's our n squared, and then this is also the 1/5. So this turns out to be tight. This is essentially an upper and lower bound. I'm going